Okay, let's get started. So this is the last topic that we need to do to be actually able to do Newton-Raphson load flow. And the only one we haven't covered is the PV bus. Slack bus, we don't have any work to do, right? Because we know the magnitude and the angle of the voltage. PQ or load bus, we have to write power balance equations for both the P and the Q. And that's a good thing because we need to solve for both the magnitude and the angle of the voltage. So we need both of those components. In a PV bus, it's slightly different. So in a PV bus, it's trying to represent what you would typically see if you were a generator. Most generators, right, they want to run as much output power as they can to maintain, their system at maximum operation. They sell the most amount of kilowatt hours, they're going to make money. So they want to schedule or set what their output power will be, because again, that's what they got compensated on. And because they can directly control the voltage, they'll adjust their voltage regulator or their excitation systems to, within reason, maintain the voltage at their bus. Okay. So because I'm controlling P and V, I have no control over my angle theta. And if you recall, way back at the beginning of the semester, we said power is really indicative or is really indicated by the angles associated with your system. So you can't control the angle. First off, you don't know what the angles are for all the other buses. And secondly, as the system undergoes changes, the angles are going to change, but you only care about maintaining that power. So you really don't want to control theta. Who cares? As long as I can get my power output that I've been dispatched for, then I'm good to go. The voltage is less of an issue, but usually the utilities require the generators to have some control of the voltage. And so they're going to try to set their voltage regulators to manage some equivalent voltage, and then they'll either output or absorb reactive power as best as they can to maintain that voltage. So we know P and we know the magnitude of V. We don't know Q and theta. And that's okay, because I don't need to solve for Q first, right? Q is based on, once I know all the magnitudes and the angles, I can calculate the Q. But the variables that I need to know the state of the system, or the state variables, are the magnitude of the voltage and the angle theta. Those are the only two that I need to be able to define the state for that particular bus. So I have one equation that I can write, delta P, which is going to solve for one value of theta. So if you come up to a system that has a PV bus, you just have to write one equation and you have to solve for one variable. That's all you need to do. Nothing more than that. Everything else is exactly the same. Whether it's a load bus or any other system, it works really well. And then you can determine what the actual Q is being injected at that generator. Based on, I have the voltages in the system Y bus, I can go ahead and calculate what the Q is to make sure that my generator isn't overextended. I'm not putting up too many bars, or I'm not absorbing too many bars. Because one of the things, if you had a previous class with me about synchronous generators, they have these, they're called reactive capability curves. And it basically shows you what the reactive power capability is of the machine based on certain power outputs. So if you're trying to push the generator harder than what it's capable of, means you could actually get some problems with the machine. So you never want to exceed those readings. So here's our system. Now we have a generator bus, which means I specify the magnitude of the voltage and the value of P. Don't worry about the Q, because that is set at 63, but that may or may not be accurate, right? So we have magnitude and angle here, and we have P and Q here. So all we did was we took our previous system and modified it by adding one additional bus, a generator bus. So we have three equations to write: delta P2, delta Q2, because those are the load buses, and I can write equations there. And for my generator bus, I can write an equation there. Now, I'm going to reorder these a little bit, because remember with my Jacobian, I want to have all my P's and my Q's in order. So my f of x equations are going to be delta P2, delta P3, and delta Q2. That's how I order my equations. Now I've got to figure out what variables I need to solve for. Well, I already know V1 and theta 1. I don't know V2 nor theta 2. And I don't know theta 3. So in terms of setting up my x equations, it's going to be theta 2, theta 3, and V, if I can move that out of the way, 2. Again, I'm lining those up in order, so when I do sensitivity analysis, I've got the partials of P with respect to theta and the partials of Q with respect to V all lined up. Because as we talked about, power flow, real power flow is by the angle theta, which we mentioned at the beginning of this class. Reactive power flow has to do with the magnitudes of the voltages. So they're most sensitive to those changes. All right, so let's take a look at the system. I'm just going to copy this over to whiteboard. There's whiteboard. It was up. There it is. Okay, so what's our process? Step 1, right? What is step 1? Build Y-bus. And the building of Y-bus in and of itself is a multi-step process, but hopefully we're pretty comfortable building Y-bus, so we can just kind of do it in one fell swoop. So our Y's are going to be all equal to negative 10J. So my Y-bus is going to be equal to, and I'll factor out the J term. So this is going to be the sum of all the J terms connected to, or the impedances connected to bus 1. We have 20, and then we subtract from it the transfer admittances between all the other buses. So bus 1, 2, bus 1, 3. It's a symmetrical matrix. So I've got my 10s there. Then I do the same thing for bus 2. And since all the Y's are the same, it's pretty easy to figure that out. Okay, that's my Y bus. Now, this is just a suggestion. You don't need to do this, but I find that this is really helpful in setting up my MATLAB. You'll notice up above, I've got a bunch of G's and B's in my equations, right? So if imaginary part of Y bus, and G is equal to, oh no, this is not going to happen again, I hope, is equal to the real part of Y bus. Okay? So I've got B equal to G, B equal to the imaginary and G equal to the real part, because I can just go back into these equations, and if I need G2 comma 1, then I just put 2 comma 1 like that. I don't have to fish it out. It just makes it a little bit easier. Don't have to do that. That's just a suggestion for how I would set up. And now I've got to go ahead and identify my f of x, which we already did. So my f of x equations, delta P2, delta P3, and delta Q2. My x variables, theta 2, theta 3, and V2. And so my Jacobian is going to have the form V2, like that. So my next step, and I kind of wrote it out, for step 2, is determine f of x's and the x's, right? What equations you need to write and what variables you need to solve for. Step 3, find the Jacobian. So over here, remember, all I'm doing, this is the partial of P2 with respect to theta 2. Partial of P2 with respect to theta 3. So the numerator terms I get from my rows, and the denominator terms I get from my columns. So again, if you do that, there's a lot of housekeeping involved with this. If you can set yourself up for success, and kind of lay these out with some organization, it makes things, I think, quite a bit easier to follow. All right. So now I'm going to be on step 4. So I'll say find the form of the Jacobian. Okay. So step 4 is start writing equations. So number 1, delta P2. And I can't remember all the variables there, so I'm just going to go back up over here. Whoops. Doesn't want to let me do that unless I do that. So let me copy this again. Let's bring that down a little bit over here. Maybe shrink it a wee bit. Hopefully this doesn't crop it. No. Okay, good. Okay, so remember, I is equal to 2, and K is going to vary from 1 to 3 in this case, right? Because we have a 3-bus system. So delta P2 is equal to V2, because I is equal to 2. Now I'm in my summing junction, so this is V1, and I'm just going to drop the absolute value symbol. Just know if I have V, it's an absolute value. All the GIKs are 0, so I'm not even going to bother putting those in there. This is B21 sine theta 21. And that's it, right? For the summing junction for K equal to 1. Now I'm going to go to K equal 2. That's it for 2. And now I'm on to 3. Minus P generated minus P delivered. So I got to go back and look up here. And so for bus 2, all I have is 200 megawatts and 100 megabar. And that's power out of the bus. So that becomes minus 2 per unit power. And that has to equal 0 when we have the right bus equations. Let's do delta P2. Delta P3, sorry. I already did delta P2. So now I is equal to 3. So that's V3 times V1, B31, sine theta 31 plus V2, B32, sine theta 32 plus V3, B33, sine theta 33, and that subtracts, is it positive or negative? Let's zoom up here. It is positive power, so it's no, this is plus, this is minus 0.3, because that's power injected. When I move the PG and the PD to the other side, I get the negative there. That's it for my 2 power balance equations, real power balance. Now I've got to do delta Q2, where I is equal to 2. So I'm going to go back up here a wee bit and copy my Q1 equation here. And bring that a wee bit closer. Shrink it down a little bit. Move it up, we'll put it over here. Okay. So I'm ready to start going. So now this is V2. Now I go in my summing junction, V1. Again, no GIs, so those are all 0, so I can ignore those. So I have minus B21 cosine theta 21. That's it for K equal to 1. Now do K equal 2. Cosine theta 22 plus V3 times minus B23 cosine theta 23. Now I subtract from that or I add to it the power demanded, which I think was 1 per unit reactive power, and that's going to equal 0. Any questions on how I came up with those 3 equations? Because that's it. All I need to do is figure out how to come up with those base equations. Feel okay? Yes, sir. If you look right here, it's kind of hard to see. I'll zoom in a little bit. That's the real power injected at bus 3, right? So we had to inject 30 megawatts or 0.3 per unit power. So now, and I don't know if we should add a step for this. I'll leave it up to you. Do you want to add step 5, simplify your equations? Or do you still feel like this is right/fine, part of the right/fine process? What do you think? Call it a separate step, or do you consider it part of step 4? I can go either way. No opinion? Separate? All right, so we'll go step 5, which is simplify. Right? That's what we're going to do, because if we can simplify it, at least for us, when we're trying to do these one at a time, it's much, much easier for us to just go ahead and simplify and come up with results. If you're writing a computer program to do this generically, you wouldn't simplify at all. You would just plug in a bunch of zeros and it would go from there. But for us, it's a lot easier to code and come up with results that are simplifying it down. So the first thing we're going to look at is V1 and V3 are both equal to 1 per unit, right? So V1 equals V3 equals 1. And theta 1 is equal to 0, right? So one of the simplifications we can do, all the V1s disappear because they're all equal to 1. So 1 times something is that something, right? Same thing with V3, right? All those terms disappear because they're 1. Now we're also going to go ahead and recognize that theta 1 is equal to 0. So you see what it says theta 2, 1? That just becomes theta 2, because theta 2 minus 0 is just theta 2. Do the same thing here. And the same thing here. And the last simplification we're going to do, we know that sine of theta 2 is 0, isn't it? Because the sine of 0 is 0. So these terms will completely disappear. The cosine of theta 2, this here becomes 1. So this term does not disappear, does not go to 0. That's a common mistake. Make sure you don't erase that term when it's cosine of theta 2 minus theta 2 or theta 3. Doesn't matter. It's the same term. So now we can really simplify. So now our equation becomes delta P2 is equal to V21, V2, sine theta 2, plus gone to 0, right? So that's gone away. V2, or V23, I should say, times V2, times the same sine of theta 23, plus 2. That's our first power balance equation. Our second one, delta P3, is equal to, because V3 is also equal to 1. So that's B31 sine theta 3, plus V2, B32 sine theta 3, 2. And that's it for that term. And so then we subtract from it 0.3. And the last one we have is delta Q2, which is equal to negative B21 V2 cosine theta 2 plus, or I should say minus, minus B22 times V2, that quantity is squared because you have V2 times V2. And then lastly, we have minus B23 V2 cosine theta 2, 3 plus 1 is going to equal 0. Those are about as simplified as I can get for my equations. Because the only variables that you should see in there that are actual variables is V2, theta 2, and V3. You see any other state variables in there? Obviously, we see a bunch of V terms, but I'm talking about the voltages and the angles associated with the buses. You see V1 in there, V3 in there, theta 1 in there. They shouldn't show up. So here's a check. When you're simplifying your equations and you're trying to take out a lot of stuff, look and see in my equations, in my power balance equation, do I have any of those known state variables in there? All right. If you look at the homework, one of the voltages is 1.04. You can still substitute in the voltage 1.04 to get your answer. So you don't need to include those. So that's a nice way sometimes of checking your work and simplifying it down. So now our simplification is done. This is important. Make sure you simplify before you do step 6, which is your Jacobian. Find and build your Jacobian. And remember, we've already specified the form of the Jacobian, so we know which partials we need to take. So let's actually start taking some partials. So the first one is the partial of delta P2 with respect to theta 2. So that becomes V21 V2 cosine of theta 2 plus V23 V2, cosine of theta 2, 3, and that's it, right? There is no theta 2 associated with the 2, so there's no partial derivative. The result is 0. I do the same thing for P2 with respect to theta 3, because I need to do that partial derivative. And over here, there's no theta 3 in the first equation, so that goes away. There's a theta 3 in here, so that's minus B23, V2, cosine theta 2, 3. My last one, partial of delta P2 with respect to V2. This is really easy. They're just the V2s drop out. V21 sine theta 2 plus B23 sine theta 2, 3. Any questions on how I got those 3 partial derivatives? No questions? I have a question for you. Where'd that negative come from? Aha, all right. Saw the negative there, but you didn't see where it came from. Where did the negative come from? Anybody? Say more.
The variable there is B2 times beta 32. You want to know that it's beta 23 would be complement beta 32?
Sort of, but not exactly. It's a calculus thing, right? If I said, take the partial derivative of 2 sine of theta 2 minus theta 3 with respect to theta 2, what do you get? You get 2 cosine theta 2 minus theta 3, right? What if I did the partial of 2 sine theta 2 minus theta 3 with respect to theta 3? I get negative 2 cosine theta 2 minus theta 3, right? Because when I take the partial derivative using the chain rule, I've got to take the derivative that's inside the sine term. It is a minus theta 3. So when I take the partial with respect to theta 3, I get a -1 multiplication out there, right? I'm not getting a lot of yeses. Remember from Calc 1? So I'm trying to highlight the fact that this is a very common mistake. You just put pluses there. you've got to be very, very careful when you're taking partial derivatives with those angles or those magnitudes out of a second, because it's subtracting the theta angle. That's where the -1 comes out. So make yourself a note, highlight it, do whatever you need to do so that you'll be aware that I'm taking the partial derivative and I've still got to do calculus, right? I can't skip any corners and just forget about the plus. So now I can do delta P3 with respect to theta 2, and you'll notice I'm going to get some negatives here. No theta 2 here, so the only term I get is here. So I have negative V2, V32, cosine theta 32. And that's it for that one. Partial of delta P3 with respect to theta 3. I've got more terms here. B31 cosine theta 3 plus V2, B32 cosine theta 32. And lastly, delta P3 with respect to V2. That's going to be equal to B32 sine theta 32. Okay. Last set, delta Q2 with respect to theta 2 is going to be equal to this is plus B21 V2 sine theta 2. This goes to 0, right? Because there's no theta term there. And then this becomes plus B23 V2 sine theta 23. The partial of Q2 with respect to theta 3, only going to be one term, and that's here. So that becomes negative B23 V2 sine theta 23. And my last one, this is another oddball one. It becomes, I got to move down just a little bit because I can't make it out. Negative B21 cosine theta 2 minus 2 V2 B22, right? Because it's V2 squared. So that's not a hard calculus thing. But again, you'll forget that. That happens pretty commonly. And then minus B23 cosine theta 23. Again, the reason why this is a negative and not a positive like in the previous case is because I'm using the chain rule. That's it. I've got my Jacobian, 9 equations that I did partials for. I've got my 3 power balance equations. I am ready to do step 7, which is the NR algorithm. And we'll put A, B, C, whatever here. Check. Or let's even go a step back. Guess your X zeros, right? Guess your initial conditions. Step 1. Check if f of x zeros equals 0. If that's the case, then it's done. You've got the answers. You don't need to do any more work. If not, you got to iterate until f of x's is approximately equal to 0. And then your last step is calculate P's and Q's for any unknown value, or bus, I should say. Not bad, right? A little bit of work, as you can see. I wouldn't say it's necessarily the easiest thing, because you can see you got a lot of work here. But nothing in here was particularly difficult. Remember I told you I love MATLAB. Now you're really going to see why MATLAB is good. Here it is. And I was actually even crazier because I didn't substitute out or get rid of V1s and thetas, did I? You can see I kept my V1s and my theta my V1, my V3, and my theta 1 in all my equations. So hopefully you all could see how that follows through. But for you all, if you want to simplify it down, get rid of those, makes it easier for you. I did it because I actually can change my initial conditions, or not my initial conditions, I can change my assumed voltages. Instead of 1, like in the homework, I can do it 1.04, and it's no big deal to make the change. Whereas if I had to do 1.04 and I had simplified everything out, it's a lot of work. So all this stuff up until line 13 is all initial setup. Line 14 is the first thing that we did in the handout. We figured out what our Y bus is. Then I actually wanted to do some conversions. I don't know why so I kept it up in voltages, but you don't really need to do it. You can do it all in per unit. And then I even calculated some I base stuff, but again, you don't need to super duper worry about that. But here are our power balance equations. And I actually wrote them out very explicitly without making any substitution. So you can see it's minus PD2, minus PG3, and on and on and on. But look at the order. I did DP2, DP3, then DQ2. And then I did the Jacobian, but I actually included a little comment here to tell you what that partial derivative is. So if you're looking at this after the fact, you can actually see, oh, that's Jacobian 1, 1. What is that? Well, Paul gave a note that it's the partial derivative of dP2 with respect to dt2 or d theta 2. So you can check all those individually, and then I update my thetas and then my voltages. So again, I'm being very meticulous, making sure I add my thetas to my thetas and my voltages to my voltages in the correct order. So again, that housekeeping is really important to make sure you set it up. And then I display my angles, just so you can go ahead and see what the angles are. And I actually did some power calculations to see what I ended up having. So you can see for bus 3, remember that is a PV bus. I'm going to tell the generator owner or whoever runs the generator, here's the amount of reactive power generator 3 needs to produce or absorb. So I calculated with Q3. I also want to look at my slack bus because that's the only other bus in the system that is putting power into the system, right? Or unknown power, I should say. Bus 3 has got a 30 megawatt generator putting power out, but P1 and bus 1 has got to put out P and Q, and I don't know what it is. So I'm going to go ahead and calculate that because I got to tell a generator, hey, you need to dispatch on to provide that amount of power. And then just for giggles, I actually calculate power flow from bus 1 to bus 2. And I actually just calculate it with the line loss. Showing the voltage drop. And then I actually show you what the line loss is. So let's run it. Hopefully no errors. And here, it took 4 iterations to get my power balance equations to be pretty low. I calculate the Jacobian. You can even see over here, right? Like, look at these numbers. The power balance equation was getting really close to 0 after 3 iterations. And then I even displayed my Jacobian. So let me go all the way up and you can see the whole results. So starts off here, way off, right? With my DPs and my DQs all off. Here's my Jacobian. And the nice thing about the Jacobian, if you have 1 at an angle of 0 for all your voltages, your initial guesses, your Jacobian is basically just your Y bus, right? These elements here are Y bus. You have zeros here and here, right? Because remember, we're not sensitive to real power changes because of the voltage magnitude. So those are 0. So you can almost partition this matrix into this, right? I've got a matrix here and a matrix here. So I can just look at my Jacobian and fill in the numbers based on my Y bus. Those numbers and those partitions, at least for the first iteration, you just get it directly from Y bus. And that's one way to speed up the results. If you don't want to update the Jacobian every time, sometimes you can just use your Y bus values and then just spit out that and go through that. That's called a fast It's a fast one, like it does it really quickly, but it may not necessarily be accurate. So you used to see a lot more of that work back in the day, but you don't see it much anymore because again, with parallel processing, you can do a lot of the stuff that you. So on the first iteration, I went from an angle of 0 for both buses to minus 1.2, minus 0.047. And if you think about it, right, I'm only putting 30 megawatts in at bus 3, so I should have a lot more of an angle drop at bus 2 because I need 200 megawatts there. So I'm going to get some difference, but not as much. I'm going to have some angle difference between bus 1 and 3, but not nearly as much as between 1 and 2. All right. So you can see my angles, my voltage drops a little bit. That's okay. Now my power balance was at 1.3. I'm sorry, 2, 1, and 0.3. Now I'm a lot closer just after one iteration, but not close enough. And you can still see, remember we had 20, 10, 10, 20, and 20. So the Jacobian was updated, but it isn't a huge change from your original Y-bus values, right? So again, that kind of leads credence to maybe I could just use my 20 and 10 values and see how close I can get to be accurate. Let's kind of keep track of that on the way through. Angles are changing and voltage is changing, but not by a lot on the second iteration. Now look at my f of x equations. They're all getting really darn close to 0. So I'm feeling pretty good about that. Power balance, my Jacobian, still kind of close to 20s and 10s, isn't it? There is some change on the other ones, but they're not that big of a difference. And we'll just skip through. Again, still pretty close to 20s and 10. And after 4 iterations, or actually 3 iterations, I'm down at 10 to the minus 6 for differences between what I expect and what I should be getting. So my final result after 4 iterations, the angle at bus 2 is minus 7.47 degrees. Bus 3, it's angle minus 2.7. Again, I should be having a higher angular difference between bus 1 and 2 than 1 and 3. And I see that there because bus 1 is 0. My voltage at bus 2 is 0.94. And I don't calculate the voltage at bus 3 because I told it what it was, right? It's going to be 1. The reactive power flow injected for the generator bus is 63 megawatts. If you remember from the slide, that's where that number comes from. So this is a load flow program that you see, and it actually shows you what the output is. So that matches what we get. The real power injected is 1.7. Is that right? That's the equation that I used here to calculate P1, right? Remember, there's a clear and a CLC up here, so there's nothing up my sleeves. When I run it, it's all legit. So P1 is 1.7. Is that right? Or is that wrong? Well, let me think about that. Bus 2 needs, what did I say? 200 megawatts, or has 200 megawatts of load. And bus 3 is producing 30 megawatts. So how many megawatts should bus 1 be producing? 170, right? Make up the difference. The power system does not have any real losses in it. There's no real power. There's no resistors in our line losses or in our lines. So there are no real power losses. So all the power, real power that's going through the system is going to be consumed by the load at bus 2. I need 170 megawatts from bus 1 and the remaining 30 megawatts from bus 2. That validates that we're feeling pretty good about the results. Q1 is going to be doing 68.2 megavars. And then again, Q3 is doing 63.4. And that does not necessarily match what Q2 load is. And the reason being is because the transmission system has reactive power losses in it. Okay. So that's why it shows up that way. And then the actual current flowing from line 1. So this is just adding some additional information. I want to see if the current through the line 1 to 2 is excessive. So it's going about 700 amps of current. Don't really care super duper about the angle. Care more about the magnitude. And then the reactive power consumed in Q1 to 2 is about 20 megawatts. And that's all the different load flow options you'll have. Questions on that? I'm not expecting you to write something like this in MATLAB because again, it takes time. So again, simplify as much as you can, but the hope is you can see it. It's easy to follow in MATLAB, right? There's no tricks. Like with my handwriting, you kind of follow the process along, but I'm writing over here and I'm looking up over here and I'm going over here. This stuff is all laid out logically. But what's the most important part? Just like you do for your exams, I did all my work on paper. I didn't just magically have DP3 with respect to DT2 or with respect to T2. I actually did it on paper and then I wrote it in here. This is my calculator. Again, hopefully you can see, right? There's a lot of information you can see and it's a little bit easier to follow. Any questions on that? No questions?
Can we give us this kind of problem on an exam?
I would give you a 3-bus system, but I wouldn't expect you to have, this much work to do. So I might, try to give you some shortcuts or kind of think about more about the process and tell me, how did you do this part of this process or something like that? Why do you think this would be unfair to have on an exam to do this much work? Well, you get 3 hours, right? No, I wouldn't expect you to do this much because again, this is a lot of busy work. And as we saw in lab this week, and actually somebody in class, they asked me to check their work. They're like, why am I getting different results than you? And they were missing a multiplier by 4 in one of their power balance equations. That's all it was. One number, and they couldn't get the same results. So it's very difficult to check this. And one of the things that I'm offering to you is if you are having a hard time doing the homework problem, I've done it in MATLAB. I can help find where your problem is as long as it's easy, because I can actually say, here's the iteration 1 result for my Jacobian. So I can send that to you, and then you can compare that with your own Jacobian and say, hey, the row 1, 2 element doesn't match yours. And I'm fairly confident that mine is correct. You can say, it must be that my row 1, 2 Jacobian calculation is incorrect. So it helps you highlight where to look, as opposed to like, I got a problem in my homework. So I've got 52 lines of code to check out with lots of characters. And it's not that many, but it is a little bit needle in the haystack because you start imagining things are there when they're not really there. So that's why this can be a lot more challenging. So again, if you're stuck, say, hey, Paul, can you send me your Jacobian results on your first iteration? Or can you give me your f of x results on your first iteration? I'm happy to do that. And then that way, that allows you to check your work. Okay. But you can even do that in your calculator. I'll give it to you in my Jacobian. If you have a calculator, I'll just say, here's what my Jacobian is after 1 iteration. And in your calculator, you're just using a bunch of numbers, right? That's all you're doing. So you can check that as well. So it works if you have MATLAB or your calculator. Any questions on that? That was a 45-minute discussion to do one problem. So I don't want to intimidate people, but keep that in mind when you're working on this stuff. It's not going to take you 5 seconds to do these problems. It takes a lot of time. Okay, but I wanted to do the full Monty. And this is only a 3x3. This is only 2 buses that you really had to analyze. It's really a 3-bus system, but it just becomes, they can get pretty out of control pretty quickly. That's why it really lends itself well to writing a generic computer program that can calculate this all at the time, all at once. So now that we know how to do it, what are the advantages? There are other methods to do load flow. One is called Gauss-Seidel, which if you can't get Newton-Raphson to converge, you can try Gauss-Seidel. I've never had to use Gauss-Seidel to get the convergence, but I will freely admit, I've only done maybe half a dozen to a dozen actual power systems analysis where we had to do a load flow. I do more of the protection side of things. And so we usually assume a fixed starting voltage, but if you were going to do more of the ISO New England like system planner work, they actually have to look at a lot more load flows. And so they have to do their runs and it just takes a long time. But it converges, right? We've seen 4 iterations and you were down to less than micro in terms of differences. So fast convergence, and they converge pretty well as long as your initial guesses are fairly reasonable and you haven't made any mistakes, right? Like you actually put the 4 multiplier, you didn't forget it. But you've got to invert the Jacobian. And if you have a million by a million Jacobian with complex numbers, or actually it wouldn't be complex numbers, you'd have cosines and sines in there. That takes a real long time. That's why you need parallel processing and you need multiple computers, and it still takes you 8 hours to do that. Inverting those matrices is very, very difficult. It takes a lot of processing power. But that's what we do. You just got to do it. There's nothing around it. So contingency analysis, this is really good because remember, contingency analysis is if we take the worst case system out, the system should still be survivable. How do you take a system out of service? You actually can automate the process, and you can see here, let's take out line 1 to 2. Let's take out line 3 to 4. Let's take out generator 1. Let's take out transformer 17. And it'll go through and it'll modify your Y bus and your power balance equations for each of those separate contingencies, and then come back and spit out a result to say, hey, everything is still good after this, or no, it's not. So you can do contingency analysis with Newton-Raphson load flow, but you got to do it in advance. You can't just do it, at a moment's notice. Yes, sir. This is Power World. If you look at the recommended book, what's that? No. So there's a bunch of different applications that can do load flow. This was developed at, I think, the University of Illinois. And it actually is something I think you can get an academic version. And it's a sort of a graphical thing, but nobody in industry that I know of uses it. It's just hard nut to crack. Aspen One-Liner is a program that a lot of people in the class are familiar with, but Aspen One-Liner isn't really used for power flow analysis either. The most common one for big power systems analysis is called PSSE. It's made by Siemens. And that is the one that most people in New England use. Also, GE made a program, it's called PSLF, which stands for Positive Sequence Load Flow. But I don't see a lot of PSLF anymore. I've seen it a couple of times, but most of the people, at least in New England, use PSSE. And they actually have a student version that you can use. But it's like, I don't know, 32 gigabyte or something like that. It's a huge download, and it's not something that I would encourage you to actually spend your time learning how to use, because the reality of you actually, having to learn it, most of the time they'll just send you to a class and you'll learn how to use PSSE. I've used it a little bit, but it's not super intuitive because, again, you've got a lot of information. But you can do contingency analysis on PSSE. And what's the contingency analysis? Really, again, it's reliability. I want my system to be reliable under statistically likely contingencies. What's statistically likely? The worst case system, in worst case fault happens, or the worst case, whatever piece of equipment you have in your system, the most important piece trips offline. That's likely. Maybe not going to happen every day, but it's likely that no matter what piece of equipment, even if it's well maintained, it's going to fail over a 60-year period. It's just not reasonable to assume. So the statistical likeliness of something like that is very high. Then you move on to double contingencies. So what is statistically likely? It's unlikely that you're going to lose an Orrington line at the same time you're going to lose a DC interconnect in New York. So you start looking at, okay, but there are 2 Orrington lines coming out of Orrington, so it's possible that the Orrington substation, there could be a bad fire and you lose both those substations. I mean, all those lines coming in and out. So that would be a likely contingency. So when you start looking at double contingencies, it changes a little bit. And these utilities and the transmission operators, which is the ISOs, ISO New England and New York ISO, at least from our part of the woods, they're mandated by NERC. So you had better make sure your system can handle these things, or else they'll fine you, they'll shut you down, they'll do all these different things. But NERC has some real stiff penalties. Even though they're not a federal agency, they're actually authorized by FERC to issue fines and all that stuff. So they're pretty serious. You got to be really aware when NERC issues things, you better follow those things for sure. So once you've set up your system with contingency analysis, now we got to make sure, do I overload any pieces of equipment? I calculated 700 amps. Is that a problem? Well, it depends on the line rating. And the line rating actually has 2 ratings. Actually, it has more than that. But the ones that we worry about, they have winter ratings and summer ratings. Kind of makes sense, right? In Maine in the winter, it's a heck of a lot colder than it is in the summer. So you can run lines at more power in the winter than you do in the summer. May not necessarily be exactly the case if you're in Florida, but the temperatures are a little bit cooler in Florida, but you might not get as much margin. And there are different limits, like there are called short-term emergency, long-term emergency, and drastic action limits, which means, you know, the long-term emergency, you get 8 hours. Short-term emergency, I think you got like 30 minutes to an hour. The drastic action means you got 15 minutes to fix it, or else this transformer is gonna catch on fire, perhaps. So the utilities will rate them differently depending on what the expectation is. And if those ratings are exceeded, people have to start taking into account and make some changes. So like long-term emergencies, those might be in the summer when it's really hot. Okay, you got 8 hours to bring the line back down. So we're going to run it hot for maybe 2 hours, and then we're going to back it off below because that shouldn't damage the line. But let's see, you can't really control the flow of power down a transmission line, except if you use what are called phase angle regulators, and that's actually controlling the phase, which thereby controls the power flow. But there is no direct way of controlling real or reactive power. It's all indirect. I adjust the voltage here, and then that changes the power flow through the system. I change a tap position, and that adjusts the power flow. The only way you can get direct control is on DC lines. They can actually directly control the amount of power because you don't have reactive power, you only have real power, and they can throttle it up or down as necessary. So remember, we want to make sure that load flow is a steady state analysis tool. It doesn't look at faults and it doesn't look at transients. So it's only good for looking at, you know, is the system operating stably, not considering those other issues. But just because it's a steady state parameter, that doesn't mean you had better make sure that your system has all the criteria being met. Meaning, hey, I need 500 megawatts from this slack bus. I better make sure I'm paying people to give me 500 megawatts. Just because my computer says I need 500 megawatts, that doesn't always mean that that's the case. And there can be all kinds of rules about when a generator is operated to provide the 500 megawatts, or maybe it's 400 megawatts and a different generator is there. So not only is it like the physical limitations of the system, but it could be emissions. Like in the dog days of summer in Boston, you don't probably want a lot of simple cycle diesel engines cranking out electricity, even though there are power needs, but you got a lot of problems with emissions. So you might have smog alerts, you might have pollution problems, which would influence which ones you're running. You also could have contracts, meaning, hey, I've got to buy a certain amount of power from this photovoltaic facility. So they have to be included, even though I'm paying more, that has to be part of the pie. So way back when we talked about introduction and the beginning of the semester, it's not always the cheapest gets on. It's not always go to the store, look at the racks and see which is the cheapest per unit quantity of whatever you want to buy. There's like, here's the price. Then there's a list of a bunch of different things as to which one, you know, what are the other conditions, if you will, that these operate on, and you got to make a decision based on that. So it really can be very, very difficult to do that. You can also do this participation factor, which includes, hey, there's some costs, but what about emissions? What about, you know, goodwill? So you can actually adjust participation factors as the loads go up and down. They'll automatically increase or decrease based on essentially a percentage. Okay, so you can adjust that a little bit. We already talked about most of this stuff, right? Millions and millions of cases, and they're getting more and more complicated with more control. Phase shifting transformers, load tap changers, switching capacitors. It used to be that when a capacitor was plugged in, it stayed in. Now you can actually have capacitors switch on and off. And I worked on a distribution circuit in Sanford that actually had a capacitor bank that could be switched in and out, which is actually very expensive because one of the things you got to be careful of when you turn on and off a capacitor, you want to do it at 0 crossings because if not, you can get crazy high transients. So switching on a capacitor or switching it off is a very expensive proposition because you need what's called an independently pole operated breaker. Each breaker pole opens on its own time frame. And so that like triples the cost of the breaker, way more expensive. So you don't see a lot of them, but there is one in Sanford that I believe is still operating. We talked about HVDC transmission and flexible AC transmission systems, thus the static VAR compensator in Chester, which is about 40 miles from here. That's when you would see those smart devices. I think we already talked a lot about indirect transmission. So change of voltage, change a tap, and then hopefully you can get power flow to go in the direction. How do you know the power flow? The sensitivity analysis. How sensitive is a power flow change at bus 2 because you change the angle at theta 3, theta 36. You can look at that at sensitivity analysis. And again, it's just one big box, right? You don't have direct control, so you're trying to monkey with things as much as possible. Here's a sort of a contingency analysis where we're looking at a power system, right? And it's our same exact system that we've been analyzing. And you'll notice that our generator bus, right, bus 3, is not doing anything. It's not putting out any real power. Maybe it's just configured as a capacitor. But we're trying to run that system and deliver the load. And look what happens. We're pushing 132 megawatts through line 1 to 2. That's overloading the line. And you can say, wait a minute, Paul, I've got 200 megawatts coming out of generator 1. Why isn't all the power, all the 200 megawatts going through the line? Well, there are networks here. There are multiple paths. Most of the power goes through 1 to 2, but some power goes from 1 to 3 and then over to 3 to 2. Electricity doesn't care. It'll go in whatever direction it can, and it balances it out based on the amount of impedance. So you can see clearly here, this line is overloaded. So let's make a change. Now, let's crank it up to 95 megawatts. Now I got this to 100% power, but this one is getting 92%. So both of these are not good conditions. One line is at capacity and one's getting darn close to capacity. So the option here is to tell this customer, sorry, I'm not going to give you 200 megawatts, which you would never do. Or you either have to run another transmission line, maybe put some generation on bus 2, a bunch of different things you can try to get that within limits. But this is what happens all the time. And then you can say, with this design, this is a really bad design because look how little power is going through that line 1 to 3. 3.4 megawatts. That's not a good use of that line. That doesn't mean it doesn't belong there. You still would want to keep the line in service because, again, for contingency analysis, if that line fails for whatever reason, you still would like to have the load delivered, but now you get some serious changes and challenges to your system. So you can see how, you can do a lot of different things. Anybody have any problem? There's 95 megawatts here, but 98.4 megawatts there. Does that make any sense? Sure does, because you got 3.4 coming over here. So the 95 plus the 3.4 gets you to the 98.4. So again, kind of the interesting thing about power systems, like, wow, why isn't only 95 going? Because you have another path to go for power. The power is coming from the utility. And the lines don't care. They do care if you're overloaded, but they don't care otherwise. So this system, and again, it's a very simple system, is you've got problems. But in reality, you would never get this to this point because the planners would be projecting out what the load is going to look like at bus 2. They can say, whoa, in 5 years, bus 2 load is going to be 200 megawatts. Our current system really can't handle it. So at that point, they're going to go ahead and say, all right, well, the load's going to increase to the point where our system is over capacity. So somebody's going to have to do some upgrades to the system to be able to continue to support that. So well in advance of that, they would have to do that. But like, Tesla, this was a few years ago, they decided to build a brand new Tesla factory just outside of Austin, right? That is not, a trivial, no big deal. Because all the utilities have to be reconfigured. Water, water supply, sewer, right? Because there's a lot of people working there. You need to get rid of the waste. But electricity is sometimes the worst. Think about all the upgrades that they would have to do. It's probably like, I don't know, 4 gigawatts of power demand. And you just can't build that in a day. That takes years. If it was in the Northeast, it would take you 10, maybe 20 years to get gigawatts of power. In Texas, the rules may be a little bit different. They might approve things differently, but it's getting harder and harder to get these projects built. So you can increase the voltage, but then you have major expenses to upgrade the system. Or you can do other things, which is interesting because like a Tesla coming to town seems like a great idea, right? But we as taxpayers have to pay for all the system upgrades. They're getting power at the same rate we are, but we had to pay for 5 gigawatts of system upgrades, not Tesla, but the consumers that live in that area. So sometimes it's a good thing, but there are some trade-offs that you need to understand and think about. And I would be highly suspect if Tesla said, sure, we'll pay for all the infrastructure upgrades to get this factory built. I'm sure there was some negotiated where the towns kicked in some money, and the state of Texas probably kicked in some money, and probably the federal government did some stuff like that there. But any energy intensive industry that comes to town, if it's new, it is a big transition and a big effect on the system. Last topic. So ISO New England is separate from New York ISO. They're their own little entities. And what ends up happening is sometimes they will transfer power between the two, which is perfectly fine. The lines can handle it. But ISO New England doesn't pay the generator owners or the generator producers or the power producers in New York. And so that all has to be negotiated with New York ISO. And they have these T lines and they monitor the transmission lines, and they actually will automatically adjust the power. So if it's contractually agreed to, then no problem. If it's not, ISO New England might say, well, we're going to start monkeying with voltages here, so you can't get the power that you want. And if New York ISO still monkeys around and tries to force the power, then ISO New England says, well, we're going to open the breaker. We'll just isolate from you. So that's a pretty extreme. All the ISOs are encouraged to work together, right? Because if they don't, then the costs increase. But there's a lot of like negotiations and stuff set up. And then once everything's set up, it kind of happens automatically. But it is a factor to consider because Hydro-Quebec sends us lots of power into New England and also into New York. And so do we transmit power between the two? We may. We just need to make sure that it's all characterized properly. And here are the balancing authorities across the US. You can see ISO New England. I guess they tried to save a letter. Same thing with New York ISO, but those are the big ones on the East Coast. Remember, Northern Maine is not considered part of ISO. You can see it goes to a circle outside of the US in New Brunswick. They have their own different ISO, but you know, we take care of most of it. Hydro-Quebec's right in the middle of all the DC lines because they don't want to interconnect. Then you can start to see a lot of stuff on the East Coast. It's always interesting. Florida has all those little ones because they're a regulated monopoly and they have a lot more munis there, municipalities that take care of their own electricity supply. So they don't operate the same like we do. We have, you know, much bigger utility companies like Bangor. Maine pretty much has two, right? Versant and Avangrid. Massachusetts, that they have a couple different ones, but they're usually subsidiaries. So they all kind of own or are part of ownership of ISO New England, not ownership, but operate. PGM, Pennsylvania, Jersey, Maryland. That's a big one. TVA, which is a federal government, Tennessee Valley Authority. ERCOT, again, they forgot to put the T for Texas. And you can see it kind of breaks up. It doesn't have all of Texas. MISO, Midwest Independent System Operator. That's another big one. And then out west, you have California ISO. They're probably the largest one because California has something like 50 gigawatts or something like that for power demand. But all these ISOs, you go onto their websites and you can get real-time information about what the power system is doing. And you can see there's not a lot of power that goes between Mexico and the States, but a lot of power goes from Canada into the States. And so if you paid attention to tariffs and all that stuff, I think the commissioner, I think his name is the commissioner, maybe the governor of Ontario had threatened for tariffs on electricity purchases into the States. But all the people in Ontario is like, that's gonna make it so that we won't be able to sell our power and we're gonna go bankrupt these utilities. And so he kind of backed off. I think his name was Doug Ford. So, you know, there's a lot of geopolitical stuff involved with this when you're crossing borders and whatnot. But electricity, again, it's just simple, doesn't care. It's all the other stuff in the background that really we need to consider. Okay, any questions on load flow? Yes, sir.
Well, it's not a load flow, but how does a regulated monopoly?
Regulated monopoly. So a regulated monopoly, the difference is they own the generation, they own the transmission, and they own the distribution. So they manage everything themselves. So they set the prices and all that stuff. And in a deregulated market like what we have, you can't have generation owned by the utility companies. They want to make it fair that way. That's the difference. So really quickly on Monday, you're actually going to have a power flow lab. So you've got to actually do a power flow, so more practice. And then a week from Monday, you have your second test, right? So be aware, take a look at that stuff. Go from there. Any questions in TV land?
Have you picked a day for review?
Yeah, the review will probably be, I think, on Thursday. I think that's typically when people want it.
Okay.
So it'll be a week from today, I believe. Nothing else? All right, folks, have a great day. We'll see you on Monday. Take care, everyone.